The energy transition is often framed as a race to produce more electricity, more solar panels, more wind turbines, more batteries, but history suggests something important. The largest companies in an industry rarely make their fortunes producing the commodity itself. Instead, they control the systems that organize, coordinate, and optimize that commodity. This video explores a structural question. As the energy system evolves, where will the largest companies, the next generation of energy unicorns, actually emerge? Because the answer may surprise many people. The biggest winners in the energy transition may not be the companies selling power at all. Solar panels produce electricity, wind turbines produce electricity, batteries store electricity. These technologies are essential to the modern energy transition. But producing or storing electricity does not automatically determine who captures the most economic value. That depends on structure. Across many industries, value does not concentrate where the product is produced. It concentrates where the system is controlled. So the real question is not simply who generates power. The real question is, which layer of the energy system controls how that power moves, when it moves, and how it is used? Electricity has a fundamental economic characteristic. It behaves like a commodity. 1 kilowatt-hour of electricity is largely indistinguishable from another. Markets set the price. Generators typically act as price takers rather than price makers. And unlike consumer products, electricity offers almost no differentiation. There is no brand loyalty for electrons, there are no switching costs, and there are limited economic moats. Commodity markets rarely support long-term monopoly value. That doesn't make generation unimportant, but it does shape where durable economic value tends to accumulate. This pattern appears repeatedly across industries. Consider the oil industry. Oil production often operates with relatively thin margins. Refining improves economics somewhat, but the highest value often sits in logistics networks, platforms, and global distribution. The internet followed a similar pattern. Bandwidth became commoditized quickly. Infrastructure layers became strategic, and the largest value accumulated in platforms and applications built on top of the network. In many industries, the commodity layer enables the system, but the coordination layer captures the value. Energy may be following a similar trajectory. Energy systems are increasingly behaving like technology stacks. At the base sits physical infrastructure, generation assets, grids, and storage. Above that sits a control and optimization layer. Software systems that coordinate generation, storage, and load. And above that sits demand, increasingly dominated by AI compute, data centers, and industrial electrification. Like software stacks, higher layers tend to capture more economic value, because they coordinate everything beneath them. As energy systems become more complex and distributed, control layers grow more important, and control layers often determine where value accumulates. Another structural force is emerging: supply growth. Solar costs have fallen dramatically over the past decade. Wind capacity continues expanding globally. Battery deployment is accelerating at unprecedented speed. All of these developments increase energy supply. But abundant supply has an economic consequence: competition. When supply expands faster than demand, margins compress. This is not a failure of the energy transition, it is a sign of success. But abundant energy is not automatically valuable energy. Value depends on timing, control, and system coordination. When electricity becomes abundant, control becomes valuable. Timing matters. Electricity delivered during peak demand may be worth many times more than electricity delivered during oversupply. Flexibility matters. The ability to adjust output, shift load, or store energy changes economic outcomes. Dispatch decisions matter. Choosing which resources operate at which moment determines profitability. Energy routing matters. Directing flows through different parts of the system creates optionality. In complex infrastructure systems, control is leverage, and leverage often determines value capture. A major new force is now reshaping energy demand: artificial intelligence infrastructure. Large AI data centers operate very differently from traditional loads. They require extremely high power density. They demand reliability approaching near perfect uptime, and they scale rapidly, often requiring gigawatts of power within short time frames. For these facilities, electricity is not just a utility expense, it becomes a strategic input. And when energy becomes strategic, the organizations that control energy coordination gain influence. In infrastructure systems, control points determine economic outcomes. Microgrids allow localized control over generation, storage, and demand. Energy orchestration platforms coordinate distributed resources across entire networks. Load flexibility systems determine when large consumers draw power from the grid. These control points influence when electricity moves, where it flows, and how efficiently systems operate. The more complex the energy system becomes, the more valuable coordination becomes. Because complexity requires orchestration, and orchestration is where strategic leverage often emerges. Flexibility is becoming one of the most valuable characteristics in energy systems. Dispatch flexibility allows stored energy to be released when prices peak. Storage control enables arbitrage across hours, days, and seasons. Demand response allows large loads to monetize grid stability. Load shifting moves consumption into lower-cost periods. Each of these capabilities improves system efficiency. But more importantly, they allow operators to capture value from volatility. In markets with fluctuating prices, flexibility transforms energy from a static commodity into a dynamic economic opportunity. Electricity prices fluctuate dramatically across time. Off-peak hours may see extremely low prices. Morning ramps increase demand. Midday solar often creates oversupply. Evening peaks generate scarcity. During grid stress events, prices can spike dramatically. This creates a market for timing. The ability to control when electricity is produced, stored, or consumed allows participants to capture those price differences. In other words, timing itself becomes an economic resource, and the entities controlling timing gain structural advantage. Infrastructure that controls timing becomes particularly valuable. Battery-buffered systems decouple energy consumption from real-time grid conditions. Private energy networks allow organizations to operate with greater independence from wholesale markets. On-site generation reduces exposure to transmission congestion and price spikes. These systems do more than produce electricity. They control when electricity is used, and when timing becomes valuable, infrastructure that manages timing gains strategic leverage over purely commodity generators. Scale is another defining factor. Traditional generation assets scale linearly. Each new plant requires new capital, new construction, and new permitting. But modular infrastructure can scale differently. Replicable systems can deploy across many sites. Energy orchestration platforms can aggregate thousands of distributed assets. And distributed networks become more valuable as additional nodes join. In these systems, scale creates network effects. That allows growth without strictly proportional increases in cost. And those dynamics are often where unicorn-scale companies emerge. Investors consistently favor businesses that control critical system points. Control layer companies often generate recurring revenue through long-term contracts. Their platforms become more valuable as assets under management grow, and their position creates dependencies for customers such as utilities, industrial operators, and hyperscalers. These characteristics create defensible economics, predictable cash flows, and strategic leverage. For capital allocators, those attributes are far more attractive than pure commodity production, which is why investment increasingly follows control points. None of this diminishes the importance of generation. Electricity production remains the foundation of the entire system. Without electrons, there is nothing to optimize. Solar farms, wind turbines, and storage assets remain critical infrastructure. But as systems mature, incremental value often shifts, from production toward coordination, from supply toward optimization, from generation toward orchestration. Understanding that distinction is important because it changes where capital flows and where new companies emerge. One way to understand this shift is through a familiar analogy. Operating systems do not produce the applications running on computers. They coordinate everything that runs on the system. They manage resources, they control interactions, and they enable the entire ecosystem. Energy systems are beginning to resemble something similar, a complex network where coordination determines performance. The companies that control energy coordination layers may ultimately capture the most durable value in the energy transition. Public discussion often focuses on how much power is produced, but the deeper transformation concerns how energy systems operate. The energy transition is not only about generation, it is about control, it is about timing, and it is about infrastructure that coordinates increasingly complex flows of electricity. The next generation of energy unicorns will likely emerge from these coordination layers, not necessarily from the companies producing the most electrons, but from those orchestrating how the system works. At TaBIS, we focus on the structural mechanics behind energy systems, not just technologies, but the architecture that determines how capital flows and where value accumulates. Our research explores frameworks such as virtual power plant architecture, negative load infrastructure, battery buffered systems, and the broader repricing dynamics shaping global energy markets. Understanding these structural shifts matters because infrastructure transitions rarely reward those who simply follow trends. They reward those who understand how the system is evolving beneath the surface. See you next time.